We're going to continue our talk on the volumes of solids, the washer method. So far we only have been dealing with rotating one area around the x-axis, and we used a specific formula that I'll refresh you in a second on. But this is our learning target today, the washer method, and you'll be explained why it's called washer in a sec. Okay, so basically to find the volume of a rotated curve about the x-axis, we have been using the formula, the integral from a to b of pi f of x squared dx. So this formula was from your last notes. We did this and I explained to you guys that this pi r squared, this looks like the area of a circle formula, and that's because if we were to slice down the middle of our curve, we get little circles, and that's how we're basically estimating the volume of the curve, is by finding the little volumes of those little circle segments, right? Well, little circle segments with a bit of a width there. So that's where the circle comes from, the area of a circle. To take the integral of it means we're finding the volume. So that's what we did last time, and we sum up all those volumes. That was a formula from last. But today's learning target will be to find the volume of solid that is created when you're actually this time rotating two curves around the x-axis. So instead of one curve like this formula gives us, we're going to be doing two curves now. So imagine rotating two curves around the x-axis, and here's a bit of a visual here. This is my top curve right here, this f of x. This is my bottom curve right here, g of x. If I were to rotate these two around, right, it doesn't show me the volume right here, but what it does show me is that little circle part that I'm looking at, the little circular surface area right here. And you get to see that this looks like a washing machine, right? The inner part of a washing machine. In a sec, after we do an example, I'm going to show you how the actual volume looks. As this diagram right here is just showing you a slight visual of what's going on here. But that's what it looks like when we're rotating two curves. We're going to be getting the volume of this part here. And if you imagine, the volume is coming out into 3D space. All right, so the washer method formula is very similar to that formula for finding the volume of a rotated curve, except the only difference is that r, the radius, is different. Here's the formula. So it's going to be the integral from a to b of pi. Instead of r squared or f of x squared, it's going to be f of x squared minus g of x squared dx, where f of x is the larger function. So basically, our radius is going to be the difference in squares of my two functions. You may also need factoring and FOIL in order to use the washer method. So factoring, you can use the diamond method, and FOIL comes in later on. Let's go ahead and do some example. After this example, I'll show you a visual of how these two curves look like when you rotate them. Just so you know, this is a quadratic function. Y equals 4 is just a horizontal line across the y equals 4 part on the y-axis. Anyways, so my first step here is to find out where my two curves intersect. To find out where these two intersect, I gotta first set my equations, or my y's, equal to each other. My next step, as usual, is I like to move my constants to the left side, so I'm going to subtract 4 from both sides. Next up, we factor this. You can use your diamond method to factor, or you could use the fact that this is a squared minus b squared, so that this factors into x plus 2 and x minus 2 equals to 0. So again, you got to make sure you have equals to 0 so that you can factor. Now that we have this set up, we solve for x. We get that x is between -2 and 2. So when I create my integral, it's going to start at the bottom at -2 and 2. Now be patient, as my formula is going to come up in just a sec. Here we go. Sorry, ignore this for now. This is my formula. I'm going to use it. So what you see right here is me plugging in my f function, which is 4. And then I square it minus, then I'm plugging in the second function, which is x squared, and then I have to square that too. You also notice that I pulled out my pi. You can pull out your pi because pi is a constant. I personally prefer to pull out pi because it makes my calculations easier, because I deal with pi at the end. So that's what I like to do. You don't have to pull out pi if you don't want to. It might make your calculations messy. In this step right here, all I did is 4 squared is 16. X squared to the second power is going to give me x to the 4th. Now we're going to go ahead and take my antiderivative, and then I'll be plugging in my lower and upper limits here. Here's my antiderivative. Now the next step is I'm going to be plugging in the -2 and then the +2. All right, make sure your calculations are nice and neat. 16 times 2, that's 32. 2 to the 5th is 32. This is going to give me a -32 with a negative here is going to give me a positive. So just make sure you keep track of your signs here. Pause this video if you have any questions. All right, now next up, let's go ahead and do 32 minus -32. That's 32 plus 32. -32/5 minus 32/5. That's going to give me -64/5. So you can do these separately, as separate chunks, but I just saw it beneficial to just go and distribute this negative in my head. Now I got to make sure I add these up, so I got to have common denominators. Multiply top and bottom 64 by 5, subtract. You should get 256/5 pi. So basically, the volume of this solid that's created when I rotated these two, right, gives me 256/5 pi cubed units. And I say cubed units because it's a volume. Now let me show you visually how this looks like. Let me just get out of here. So it's a cool website here. I'm going to be setting my function. So, well, usually my function 1 is the one that's equal to 4, but whatever. So function 1 is my x squared. The second function was y equals 4. It is from -2 to 2. Let me set my functions. So as you can see, there it is. And this is basically an area that we're looking at right here. What we're imagining is that we're going to rotate this area around to create a solid. So here we go. Let's click revolve. It starts to revolve now. Right now, it just looks flat, but that is because we're viewing this on a 2D surface. If I were to rotate this, you get to see that, look at this, it's a cylinder. So when I rotated these two areas, I got a cylinder here. And we're finding the volume of that. And the volume of that is what we just calculated right here on this cool website. It calculates the decimal approximation of the volume and also the surface area. But as you can see, this is what we're doing right now, which is rotating that figure and finding that volume. Oops. All right, let's go ahead and move on to example 2 now. So now let's do a very similar example. I want to find the volume of the bounded region between x squared and 9, and they're again rotated about the x-axis. My first step is to set my equations equal to each other. Next step, I like to move my constants to the left side. Next step, I factor this, and you could use the diamond method. I'm going to personally use a squared minus b squared is a plus b, a minus b, and vice versa. All right, solve for x. You should get that x is between 3 and -3. So basically, when you create your integral, you know to put -3 at the bottom and 3 at top. That's the purpose of these. All right, now I'm going to be plugging into my formula. And again, the formula is going to pop up right here, but basically it's pi, your lower and your upper limits. Then it's the first function squared, so 9 squared minus x squared, and then square that. That's just part of the formula. There we go. This is a formula that I'm using right here. If you have any questions about how I'm using this formula, you want to make sure you do ask me after this video. All right, so 9 squared is 81. X squared to the squared is x to the 4th. You basically multiply these two. All right, cool. Now I'm going to go ahead and take my antiderivative of this guy. Good. Next up, I'm going to be plugging in my lower and upper limit. Don't forget about your pi. I go ahead and I plug in the lower and upper limit. I do my calculations, and you want to go ahead and double check that Ms. Adano did this right. And you get this much cubed units. Awesome. Again, you would want to check what this looks like, but I can already tell you guys this is going to be another cylinder. We'll be also doing regions that have little holes in the middle and such like that later on. So get some practice on these, and please make sure you ask some questions if you have any.